Um, so, how do I get back to home? So the calendar that isn't updated. Okay. It reflects my understanding of the academic calendar that I am not permitted to assign homework that is due on the last day of class or any time between the last day of class and the final. This snuck up on me a little bit, but that means there's no homework this week because the homework this week would be due next Friday, which is in the band period of time. Fortunately, I was stressed out about that, and then I went and did the thing I was going to assign your homework in like 15 minutes, so I no longer feel bad. So it will simply be the lab. Then I looked at what I was going to do next week, and it looks boring, so I think I'm just going to introduce the final once I decide what the final is going to be, which is going to happen any day now, in the sense that I already knew what the final was going to be when I started this semester, and I just have to write it down. After getting burned by this once, I am going to do the final before I assign it to make sure I don't accidentally assign something impossible. And for the record, I only did that once, okay? And it was real impossible, and it took me like a long time to figure out it was impossible too. So I don't know what the students were doing while that happened. So that's what you have to look forward to. So I think I'll probably just provide this as supplemental material. I mean, it's already on the blog. It's like, it didn't look cool to me. There's this thing called bump allocation, which is as boring as it sounds. And then the next most exciting one is linked list allocation. And like, if you don't know what a linked list is at this point, like, I'm no longer taking responsibility for that. That's crazy. So that's the plan for the rest of this class. This is the last formal lecture. The lab is you implement the things we did in this lecture. Then we start the final. Yes?
So is mapping due on Friday?
Yeah. Yeah. So let's do the Friday after it's assigned. So yeah, this Friday.
Okay.
It's not that bad, right? There's a lot of text. This isn't text. This is an image. Did I write this? This isn't how I usually write things. But that's my code, yeah. Did you look at this? Is it bad?
I just barely looked at it.
Okay, do it by Friday.
I just wanted to check the
Yeah.
parts.
Yeah, you're doing great.
Okay.
A+. Okay. I think I have to do this. Did I want to do that? Okay, well, let's do this first. Okay, that's live. Okay. Yeah, I guess that should probably save you finishing up on mapping. Though I guess I think of mapping as part of page faults and tables, so maybe it was insufficiently labeled. Okay. Students, probably at this point I have taught you the heap in the way that I usually teach it, which is I've been a little surprised a few times following the blog this term, which, again, the blog seems pretty chill. Does not seem very theoretical. And to me, like, the interesting part of operating systems is the theory behind it. So you have seen me teach heaps before, and I teach them theoretically as the heap abstract data type. And usually I have you write a heap and use it for something. And so because you have probably taken this in one of the two classes, either the C class or the Rust class, I'm just linking those assignments so that you can be refreshed on them. You don't have to look at it. Today, when we introduce the heap, we are going to be doing much more set this bit flag here, set this bit flag here, set this bit flag here, populate these table entries, and so on. So it's going to be very much the actual underlying implementation of the thing that is called the heap. So let's motivate this. Writing code in our kernel so far. Have any of you tried to use a vector in your kernel yet? Did it work? Okay, it wasn't supposed to work for some reason.
Oh, I implemented implemented an allocator already.
So that would be why it worked, because you implemented an allocator. There. Okay, so did it work before you implemented an allocator?
Well, I didn't try because I knew it wouldn't work.
See, exactly, right? So vectors are like pretty okay. I'm not really into reference counting in boxes personally. Some people like them. But anyways, if you've gone and tried to use if you've gone and tried to use a vector at some point now, it has not worked. If you've gone and tried to use an arbitrary precision integer, it has not worked. If you've tried to use a big S string, it hasn't worked. What all of these things have in common, I'm thinking way back to the olden days when I first started teaching Rust, is these are the arbitrary size data types. These are the data types that have borrowing implemented on them, so you have to clone them if you're passing them around and stuff. So none of those have been working in our kernel yet. The only things we've been using is we used local variables up until 5 minutes ago, and then finally, because this was the next lecture, I allowed the use of a static variable last class. And there was, simply at that point, no longer a compelling reason to work around the use of a static variable. So local variables live within the same regions of memory that are used for the function that controls them, so the function that you call. And so the only thing you have to do to support local variables is you have to support function calls. We already know we support function calls. That's the compiler's problem. The compiler's been working just fine for us this whole time. We will learn about compilers some other day in some other class, right? So it has probably been unsurprising to us that we're able to use functional variables. Now, at some point in every computer scientist's life, they attempt to return something from inside of a function that only exists on that function's call stack. What happens in that case is the function call stack exists somewhere on the big stack, so I'm gesturing with my hand in open space here. You hit a return statement. It blows up the call stack of the current function. What does blows up mean? Different things in different contexts, but basically that memory is deallocated. So reads to it are illegal. Probably the information you're talking about is still there. You hit a return, which means you go back to some other memory location in instruction memory, and then you start executing instructions. Those instructions expect to see some return value. They look up that return value. That return value is at a location on the call stack that is too far beyond where you're supposed to be reading. So it is an illegal memory access, so the operating system swoops in and stops you. You are the operating system, so you are now responsible for this. The other version of this is, I think this is much easier to think of in terms of static commute, but static variables in general. Static variables are stored at a fixed memory location for the complete lifetime of the program. So what does this mean? When your program comes to life, it's going to require some certain amount of memory footprint within your device. And simply the memory footprint is expanded by however much size you need for each of your static variables. So each of the static variables have a fixed location in the current executing process, and you can always refer to that location. By default, these static variables are not things we're supposed to update. Why is that? Well, Rust is convinced I'm going to write multi-threaded Rust code, which I haven't gotten around to yet. So I'm convinced no one else has ever done it either. But if you happen to be writing multi-threaded Rust code, and then you have a static variable that is in a fixed location in program memory that everyone can read and write, then two different threads can try and read it and write it at a different time, and that is the negation of thread safety. Rust is into memory safety and thread safety, so it tries not to allow that, so static commutes are considered bad. I avoided them being bad by only writing single-threaded Rust code. And then we're just going to kind of pretend that my interrupt handlers can't run at the same time as my main, which they currently can. So it is true that I maybe have multi-threaded Rust code, but we don't need to talk about that in polite company. Okay, the call stack is a hardware-level stack ADT. This is less true than it used to be, but the manner in which it isn't true is the red zone thing that we struck from talking about in this lecture because it seemed too complicated. And I think I basically agree with that. Suffice to say, in actual existing physical hardware, they're no longer using a stack. They're using an array. But the idea of using a stack has persisted up the abstraction hierarchy to us as programmers who are not actually working in physical hardware. And it has persisted across time because initially devices were working with a stack ADT and could only reference the stack. So what do stacks do? They support push and pop operations. And someone always asks, No, they don't support a peek operation, okay? Peek is assembled by doing a pop and then a push, okay? So peek does not exist. It's an illusion. It's just like -0. It's not really there.
I mean, like, not uncommon is a combination of common and not, but it's also a complete thing in itself.
Yes, but peek is not like uncommon,
Okay.
because there exist things that are uncommon, but there do not exist the peek operation for the stack ADT.
Okay.
Yeah. I regard the stack as being an arrangement between the compiler and the hardware. The stack is set up by an executable, including a bare metal executable, such as the operating system. The stack is not naturally occurring, but there is hardware level support for the stack, and the most prominent case of hardware level support for stack is with the stack pointer, which is usually the RSP on the x86 device. And so hardware is set up expecting code to be written for the hardware that expects there to be a stack. So there's this sort of convergent evolution between compiler technology and hardware technology. The OS doesn't really care about this as much as the compiler does, and so we haven't really focused on it particularly this term, and I haven't necessarily found it particularly interesting. Now, setting up a stack is an independently interesting thing to do for sure, but it is fundamentally a compiler's topic. We should quickly refresh ourselves on the call stack. Also heard these things called stack frames.
I talked about that a tiny bit.
Great. Okay, this is what they look like. So we have here the metaphor of an inner and outer function. They're helpfully named. So I am executing some outer function. The outer function has a stack frame that is pushed onto the call stack. It has an X and it has a Y. So memory space is reserved for the Y, but the Y is not populated because another call occurs. The call occurs by pushing the parameters onto the stack. So that is I, which is, that's a U size? Oh, because it's an address. Okay. That's weird. Okay, so we push a parameter onto the call stack. It's 1 because X is equal to 1, so we push I equals 1 onto the call stack, then we push our return address onto the call stack. Then inner is going to write, these are called arrays in Rust, right? That's an array?
Yeah.
Yeah, okay. And since that's an array, it doesn't have any of the delicious sauce that accompanies a vector. So we just push it directly onto the stack as 1, 2, 3. Here it is, 1, 2, 3. These are pushed on immediately after the call stack is set up, so there's no sort of intermediate values there. Then what happens? Okay, now we're going to attempt to return, and for some reason Rust programmers are allergic to writing return, which I don't really understand. But anyways, this would properly be written as return space Z open bracket 1 close bracket semicolon. But you can write this if you want to. Probably everyone will think you're cool if you write it this way. Is that true, Jimmy? Do people think that's cool?
It's standard at this point.
But is it cool?
Yeah.
Okay, it's cool.
I originally was like, I don't know, but I've slowly started. I don't write return anymore unless I do like an early return type thing at this point. It's infected me.
So I'm not going to rant about this too long, but how visually obvious is it that there's not a semicolon on this line? That's what I want to know, right? Like, did that jump out at you? Or have you maybe spent your entire life going back and forth between programming languages that do and don't have semicolon terminated lines? That's my opinion. And for how much syntax this accursed language has. Okay. What they should actually have is they should have an emoji that represents return. And it should be the 100 emoji. Okay.
Sure.
Because this has Unicode support. Okay. All right. So this is the call stack after outer has called inner, but before inner has returned. The outer variables are higher up. Inner variables are lower. It begins with parameters, return address, and then other things. Inner has pushed its local array. Okay, then what happens? Okay. So when we're done, when the sort of inner call finishes, what happens is somehow this 2, this delectable little 2 here, that is at location 1, has to end up wherever y was created with outer. Now, we should not necessarily think of x and y as keys in a key value pair in this case, except in the case of compile time. In practice, the machine level code is not going to refer to x and y by these names, but they're going to refer to them as either absolute or relative locations on the call stack. So the presence of x equals and y equals is, that's sort of useful maybe from a human readability perspective, but in point of fact, these are just numbers that are persisting on a stack somewhere. The variable names are a useful abstraction, and they're a compile time abstraction. They do not exist at runtime, most likely. So they do not exist at runtime. There are just numbers on the stack that are being moved around. So every time you think you're using a variable, you are, but the computer is not. So after the inner function returns, its part of the call stack is popped. Everything is popped off. And that includes the return address. And when the return address is popped off, it's going to be some kind of special pop that is also going to return control flow to that location. Only the local variables of outer remain. The local variables of inner are gone because they're part of the inner call stack, and that memory is deallocated or freed or no longer considered valid. Variables persist precisely as long as the function that creates them. And in Rust, we have something one more specific, which is we have non-functional scopes. So you can do the little brackets inside a function, have a temporary scope. So they persist precisely as long as the scope within which they are created. We can test this with Rust. The Rust compiler enforces these lifetimes. It throws an error if we try and break the rules. So let's see if we can get this working here. That's weird. Okay, I want both of them up at the same time. Okay, so we can get a little source main going here. I can create inner. Wait, why am I typing this? This is not an interesting thing to type. Okay, so here's inner. In this case, what are we doing? We are creating an array. This array will exist in the inner call stack. We are going to return a reference to it somehow. There's a bunch of nonsense here. And then we're going to try and look at that reference. So main is going to be our outer. Trying to remember how to use Vim. Okay, so let's see. We'll do say x equals 1, y equals inner x. How do you print things? It's like this, maybe? What language was I writing that I don't remember how to write Rust? I feel like I've only been writing Rust. We'll print y. And then we're going to return unit. Okay, I'm very surprised I don't remember how to write Rust. Okay. X is not found in this. Oh, okay. It was JavaScript. We figured it out, right? Why was I writing JavaScript?
Why were you writing JavaScript?
That's the only language it could have been. I don't know what I was writing JavaScript for. Oh no. Okay, here. Oh no. Oh, this is so unexpected. I was sure that I would be able to pass the address to an array that no longer exists back to my main function. But the mean Rust C compiler didn't let me do that, just because that memory no longer exists. Okay. And so what did we learn from this? That Rust is bad. Okay? Okay. You all have hands. You have at least one hand with 5 fingers. Hold up the number out of 5 that Rust is. What did you go for, a 0?
Wait, it was 1 to 5 on the scale, right?
Yeah.
Oh yeah, I think Rust is horrible.
Okay. But you like Java?
I love Java.
I'm agreeing with a Java programmer.
Yeah, I'm giving it about a 4.
It's not perfect.
3.5 is fair.
I can go as high as 3.5.
I like that.
I think I can't separate my distaste for cargo. Oh, let's get a number for cargo.
I haven't been tracking what your specific view for cargo is.
Calvin hates using other people's code. Turbo makes it easy.
That's true.
That's not what I thought I hated about it. Okay. Okay. So okay. Hypothetically, say you want to be able to do this. I don't know why you want to do that, right? This is the problem. When I got into memory allocation, it was always because I was trying to return pairs of things. And so the thing that really convinced me I want to do memory allocation is I was trying to return a vector of length 2 of 64-bit floats. I was doing some computational mathematics. And this is just like an absolutely miserable thing to do in C. You're either allocating memory or you're like passing arrays into functions and they're like, load. It's terrible. There's no good way to do it. So one option is the static variable. I can say, hey, you know what? I'm just like always going to throw my values into this like fixed memory location that exists in program memory somewhere. So we can do that. Do we care about static variables? I don't think so. Oh, yeah, we wanted to shout out the linker. So you all remember the linkers because Jimmy taught you what they are. Probably.
I mentioned that they were, at least I...
Okay. So like a lot of times when we're not basically in a compiler's class, we just like wave our hands and say the compiler does X. But oftentimes when we say the compiler does X, it's actually the linker that does X. And so linkers are responsible for stitching together machine level code, among other things. So statics live for the complete lifetime of the program. So how are we going to make a static? Not too bad. We're going to break up our declaration, and we're going to have a static Z. So we're going to capitalize it following a convention that I don't actually hate in this case. So, okay, for just a little tiny rant, if you'll indulge me. There we go. That's the term. I have seen Python code where people have written all caps variable names, right? And they're like, oh, it's a global. No, that thing is exactly the same as every other variable, right? In this case, Rust, okay, I'm getting off of 1. I'm up to like 1.5 here. In Rust, it's actually a different kind of thing. So it is a different kind of thing, a static. And so when we use a capital Z, we're referring to a different kind of thing. So let's do the different kind of thing. So we need this Z to somehow persist forever. So we're going to static it. We're going to capitalize it because it has global visibility. Now, we cannot naively just say this equals 1, 2, 3. And I think I can demonstrate this. Okay. When we create a static, the compiler, I like this about Rust 2. We're up to 2, okay? As we start at 1, I got moved up to 1.5, now I'm at 2. Okay, the compiler is going to enforce that I need to declare the type for a static variable. Now, we're back down to 1. For some reason, it wants me to declare this as an I32, which is clearly wrong because here on the slides that the Rust C compiler should have been able to read, it says U32, which is also wrong. These are clearly U64s. So we'll make them U64s. I mean, internally in program memory, there's a virtual certainty those are U64s, right? Oh, I forgot how Vim works. Okay, does anyone know Rust? It's like maybe this?
Yeah.
Is that this? You've all done this before? Oh, okay. That's why it was U32. Oh, hey, wait, is that what I was trying to do? Yeah. Okay, so this is exciting, right? Sorry, I have to change one thing, and you have to be patient with me while I do it. Okay.
There we go.
Oh my gosh. Okay. I forgot how to type. How do you write semicolons?
What, with the key?
Okay,
On
hold
the
on.
keyboard?
Hold on. Okay, I'm deleting this. I'm going into insert mode.
They are helpfully labeled with the
Oh, you don't-
R.
I thought you had to do shift to do a semicolon. It's the default.
How did you... What?
What? Have you been replaced with the failed clone?
Am I usually this unhinged?
I feel like 1.25 times more.
Like, if
It's
we're
like
not,
different fonts.
if you were 0 on Hinge, I'd be more worried.
It's a number.
I did forget how to type semicolons.
That was weird. That's
Which is a weird thing to do when the specific thing you're trying to do is to type a semicolon that you don't have to type, right? I was like, oh, I want to type a semicolon. Okay.
Yeah, even if you have even if you do have return, I don't think you need a semicolon at the end of that.
It's a Monday.
You might.
I wanted a semicolon at the end of it.
I know you did.
And if you put a colon there, it definitely doesn't work. Here, we'll check. I don't know how much teaching we're getting done today.
No, says the compiler. We don't allow full colons here, only partial ones.
Which is so weird because there's more of the semicolon, right? It has additional sauce. Like, look at,
That's true.
right? The full colon should be 2 commas stacked on top of each other.
Well, if you view the period as like a, I'm stopping, and the comma as like a, I might stop, then the replacement of one searching thing with a maybe thing makes it more semi.
But then why don't you replace the top one?
I don't know.
Anyways, this worked. I don't know if you saw that. I'm able to write Rust code. Okay. When the inner function returns, its part of the call stack is quote destroyed. I don't think it's literally destroyed, right? It is, so when at the end of the first stage, when the Valar cast the Dark Lord Melkor beyond the Wall of Night, right? They didn't destroy Melkor. They put Melkor in a region of memory that was not currently allocated, right? And so from there, no one could successfully address Melkor, and then Melkor could not unmake the world, right? And so this is a reasonable way to deal with your problems. So probably, if you think of yourself as being like the army of the Valar at the end of the first age, that's what the OS does, right? Should we do like a Cimmerillion class next term?
Oh yeah. Probably not in the CS department.
Why not in the CS department? It's related to CS. I just gave an example.
Well, I don't think that, in this analogy, I don't think the call stack that we're like destroying is actually moved anywhere. We just like ignore it.
Maybe this is off topic. Maybe they moved Middle Earth and left Melkor in the same place. Okay. Okay. So canonically,
It's in the appendices.
canonically, the reason the Earth is round, right,
Yeah.
is because it was flat, and then at the end of the Second Age, the Valar curved it into a circle or a sphere. You almost got me there. Okay. And this is why you can no longer reach
Elf heaven.
Valinor,
Yeah.
by sailing to the east, because it's east along a tangent line, not along the surface of the Earth,
Yeah.
right? So that's kind of moving Middle Earth away from Melkor, right? I think we could all agree.
Honestly, sure.
I'm technically correct, the best kind of correct. Okay, so Melkor is much like a static variable. Lives in a separate memory range that is never destroyed. The and Z1 reference is still valid after the return because it's referring to Melkor, who has been placed beyond the ability of any practical means to be destroyed. Okay. This resolves an earlier error. I think it's kind of weird, and I don't have a counter proposal to this. I think this is weird, everyone. It's kind of weird that you can refer to something by name that is not defined in that function. But I get that it's like it's defined in the global namespace, right? So inner exists in this global namespace, whatever. Now, a clever student would ask, what if I declared this in a different file? Then what would happen? I don't know. You can check. Okay. These are read-only by default. Here, I can demonstrate that. See, not allowed. I'm not allowed to write to them. And then what happens?
Then you can do whatever you want forever.
Nope.
Nope, you have to say it's unsafe.
You have to say it's unsafe.
Because Rust is thinks it's your mom. I don't know.
Shout out moms. Okay.
Shout out moms. What? Do you need a semicolon? No, there we go.
Wish I knew how to write Rust. Okay. Wait, no, don't. I know Rust. Look, it works. Okay. Should that have worked? No, this is extremely dangerous. Obviously, that's why it's in unsafe blocks. Okay, so get rid of these unsafes. Then we're fine again. Okay. Oh, yeah, you're supposed to put these in mutices. That's for the networks and concurrency class. Would that not be the plural of mutexes?
Mutexes or mutices? I'm personally fond of mutices.
I feel like if I'm gonna say mutexis, I have to like put on a cowboy hat and wear some cowboy boots, and like have opinions about the Alamo that are not consistent with my DEI statement. Okay. Okay, so this is not related.
Most people say mutexes and not mutices.
The only
Well, most people are wrong.
The only directive is to remember the Alamo,
Yeah.
not necessarily have any particular stance on it. I remember the Alamo; it was good.
If I were elected Immortal God Emperor for life of Tejas, then we would there would be mandatory opinions about the Alamo. You would get to select from a series of opinions. Okay. Local and static variables enable most use cases. I don't know what most means there. This sounds like something an LLM spits out. You're like, yeah, that sounds right. Okay, an LLM did not write this, by the way. Now, in my previous class that I just taught, I did have an LLM write the lecture for that class. And it was actually pretty good. Okay, however, they both have their limitations. Local variables cannot be returned, and static variables cost money in the sense they cost memory. I have been persuaded of the following by anonymous accounts on Al Gore's internet, which is that I shouldn't need as much RAM as I do in my computer. The reason I need RAM is because everyone that's writing code for my computer doesn't have to pay for the RAM in my computer, but they do have to pay for the RAM they have to use on the cloud. I found that extremely convincing because I was like, why in 2026 do I need that many gigabytes of RAM when everything runs on a cloud data center? And so I've been convinced of this. You can think about this what you want, but it's good to think about these things.
Are you the same person who wants every single numerical variable to be 64 bits?
No, I don't want that. The hardware wants that. It prevents fragmentation. Yeah. No, I think every single variable should be ternary. And how many trits do I think it should be? 9?
You tell me. What do you think?
Probably 9.
I like 13. It's prime. It's got swag.
Some people have considered that.
Are you kidding me?
I'm sure they've considered it.
People can throw out any number they want for ternary. It's the Wild West.
That's terrifying.
I mean, there were plenty of computers that worked just fine with 7-bit precision forever.
Yeah.
Right.
I mean, 11 bits. There were some 31, 32 byte computers.
Yeah.
17 byte.
I mean, 30 is great, right? 30 actually has a lot of nice properties because it's divisible by 5 and 6. And 3. I have historically motivated allegation with variable size types. Locals and statics are fixed size. Examples include arbitrary precision integers and Pythonic lists, 2 things that are in Python. So absolute geniuses will note that probably on some level, Python uses the heap. This is possible. No one's ever looked at the Python source code, so we don't actually know how it works. Okay. It's called dynamic memory. Yeah, I feel like because of the prerequisites for this class, you know what dynamic memory is already. That's how I feel. But I'm going to remind us what it is. Okay. It is dynamic in the sense that it is impermanent. I have heard dynamic memory described as follows. It is beautiful because it's transient, right?
Did you say that?
Yes, I said that. That is an exact quote from me.
Presumably Calvin has heard the words that come out of their own mouths. They have heard it described that way.
I watch all my lectures after I make them. It's been a kind of dark time for me lately because I've run out of my own lectures to listen to, so I've been having to listen to other things. And people send me stuff, like some of you do this. students are always sending me videos. They're like, hey, watch this. And they're all like 3 hours long. And I don't care about them. Or that's not true. I care about everything you send me. Okay, just for the record, everything you send me, I watch. Okay. Okay. So dynamic memory, which is beautiful because it's transient. What makes it transient is that it is allocated, which is sort of like when the Valar sung into existence Middle-earth. And it is deallocated, which is what happened to Middle-earth at the end of the Second Age, right? So, it can be here for a while, and then it's gone. It's gone means different things in a security context, which usually means it's not gone. So just be aware of that. I would actually go so far as to say in a security context, it's there forever, right? And then in a can I use it? So it's like your enemies can use it, but you can't. It's kind of like liberalism. Okay, so here is a visual example. The examples are silly, okay? So we have an inner function. We can start with the outer function. So also I can't run this code because I haven't written allocate and deallocate, right? So we have an outer function, blah, blah, blah. We're going to call inner on x, okay? This makes sense to us, probably. We're looking up something in a table or something of this nature. Okay. Inner is going to return a mutable reference to a U32. Why does it have to be mutable? Because we're going to dalloc it. Oh, I had a question. Okay. Are there marker?
Somehow there are no marker.
Okay. So I saw this word earlier today, and my brain split clear in twain. I don't know why I didn't just write it over there. That's probably closer to all of you. Okay. So I saw the term, do not pronounce this. That's part of the thing. Okay. Right? Okay, so we see this. Now I'm going to write words on both sides of it. Okay, so, right. So if I cover up the top word, how do you pronounce this?
Relocation.
And then if I cover up the bottom word, how do you pronounce this?
Reallocation.
Isn't that fun?
Or you could pronounce the top one, deal locate, deal left.
This could be deal location,
Deal location.
right? Yeah, or like feel location. I don't know.
Buying drugs.
So anyways, I was looking up memory management, and I was like, why are they talking about real locations all the time? These are all virtual addresses, right? And this is why I don't use this function. I just always use malloc. Which this I use because it's similar to calloc, which is Calvin location.
Mm-hmm.
This is Mallory location, I think. Okay, so Z, which is 3 U32s, or 64s, if you want to be normal, is borrowed from the operating system, populated with values, and then a pointer into that location, so a pointer to this location, is returned to this outer. Okay. An astute learner will note that there is a complete disaster unfolding before us, which is we deallocate only this value, which means we are still occupying effectively the same amount of memory unless someone needs to use 32 bits of memory, which they don't. My claim, this would have a smaller memory footprint if you allocated 64s, because then you'd be getting a free 64 back every time.
That's actually a good argument.
So it's not very good, actually, because this would still use 128 per time, so it's actually neutral if you can reuse the 64s, so, which is why you have to check your linear combinations before you make claims that aren't true. Okay, so inner stores Z to heap. You return a raw pointer. You actually return a mutable pointer. You can write this using pointer write, which we taught you at some point this term, probably. You can use offsets. Anyways, this is deal located. Okay, this is what it looks like. This is extremely bad, obviously. We see how this is obviously extremely bad. It's fragmented memory. Okay. The Z1 slot is free again and can be reused, which is completely unhelpful to you. This is a memory leak and is bad. I should have capitalized the B in bad. This is basically bad by definition. Like, when you think of things that a program could do that's bad, leak memory is like the thing. One other thing you can do, and I love doing this, I do this all the time, is use after free. I suspect Rust prevents you from doing this. Anyways, when I teach C, I always show a use after free, and it usually works just fine. Oh, do you have a question?
When you deallocate it, probably the name doesn't work anymore. If I say deallocate X, you can't just say X again.
Yeah.
So how do you have to like point at the memory? You figure out
Yeah. You take this pointer.
Yeah.
Or where's the pointer? Right. So this thing is being returned as a star mute U32.
Oh.
I cast that to a U size. I save the U size, I deallocate. Then I cast the U size back to a mute U32. And then I look up the memory at that location. And probably the value is still there.
Yeah.
And you have to do that all in an unsafe block. Okay. Quote, writing memory safe code is hard. Apparently, blog claims there was a use after free bug in Linux as recently as 2019.
I know a lot of memory bugs in Linux still.
That's, yeah.
Most of them don't allow for like actual like full getting access to like the system or like privilege escalation, but most of them result in like you can like deny service, which is still considered for the Linux kernel a pretty bad thing you can do over the internet.
Yeah.
Because you could just shut down a remote server whenever you would like, if that's something that you can do.
Mm-hmm.
Still not good.
Yes, and it's unclear if it has more or fewer vulnerabilities than any other kernel as well, which is the other thing I always get into. It's like, we don't need to turn this into a lecture on security by obscurity, but you can look that up if you want to. Here's a claim that I do not stand by. I did not say this. Do not quote me on this. Absolute cowards use Java and Python to solve this problem. And so I wrote that, and what did I do? I made it less mean by saying people other than absolute cowards also use Java and Python.
There's at least one absolute coward who uses Java and Python to solve this problem.
Yes. It's me. Okay. Well, I don't use Java. Okay. Rust allocation, deallocation. I think we all know this. It's handled using ownership and lifetimes. Which basically means scope and then also variable name things. We have, in one of the classes, we used box to manage memory manually, which was probably kind of unexciting. I'm looking at the time. Okay, so here's the problem, right? So we all established my brain doesn't work today.
Mm-hmm.
I neither know when class started nor when it ends.
Ends at 2:40.
And I also can't do subtraction right now.
We have 40 minutes.
Thank you. Do you think we can make it?
Yeah.
Okay.
I think we're going to get through more of it.
Let's keep talking about it.
What?
It's not function signature for drop.
What?
And that is one of the drop is weird. There's two different drop functions. One that takes. You should look at the code for that drop function. Look at the code. What do you think it does?
I don't know how to look at the code.
You just click source.
Where do I click source? Oh, here?
Yeah.
Whoa. Okay, so when you said source, my brain transcribed that as lowercase src, just so we know. Okay? All right.
Yep.
Yeah, that makes sense, right?
Yeah. It's empty. I love that. It's not. It's just empty. It just takes ownership, and then once you take ownership of it, the lifetime's over. So once the function's over.
So I believe this is Indy's favorite function, so you can ask Indy about this. I would have just called it free. That's the only thing I would have changed. I was singing Freebird in class this morning. I can't sing. So like a lot of times you commit to it and you're like, ooh, I'm in like the middle of a verse and I have to get to the end and I'm not going to like learn how to sing in between now and then, right? So try and not ever goad me into singing. Okay, so we can write a use after free.
It seems like you have to do a lot of really specific and obviously bad stuff to make a use after free happen. It doesn't seem like the kind of thing that would happen on accident.
Oh, it happens all the time on accident, but it happens under more complex
Yeah.
management.
Once you start doing more complex code, it's quite easy to accidentally return a pointer to something that,
Yeah.
or use a pointer that's already been created. Because once you have like complicated things where things are freed in this branch and things aren't freed in this one because they keep living, then it can get pretty easy to do that.
Fair enough.
Oh, right. This thing isn't allocated, so I can't drop it. Is this gonna do it? Yeah, okay, I think that did the bad thing. Okay. Drop takes ownership. That signals to the compiler no one else can ever use the thing. So when drop takes ownership, it passes beyond the wall of night. And then your code explodes. But if I get rid of this, then it's fine because no one's using after free. And if I get rid of this, that's fine because no one's using after free. So there's a different drop, Jimmy? Is it interesting?
It's just the drop trait also has the drop function, and that one is the one that actually runs all the code cleanup and takes immutable reference to self.
Okay. I also linked that, so go find drop if you're interested. This code works. Well, okay, we'll look at it. What? Okay. Wait, did I paste twice? We'll look at it.
No.
So this is allowed. I'm allowed to box things, print them, then drop them. I'm not allowed to drop them, then print them. Man, that message is so long, it doesn't even fit on screen. That's shocking to me, right? Okay.
Rust tends to use a lot of space for stuff.
Yeah, like this line is not really doing a lot for me. This line's not doing a lot for me. I don't know. This is not doing a lot for me because I don't use nightly because I'm not a huge nerd. I mean, I use nightly for this class, but this class is for nerds. Okay, so this okay. It's okay to drop things when you're done. Now, if I were being extremely pedantic, which I've thought about doing, really, you should have to drop every single thing you use that's allocated before you return, right? That would be cool, right? And so, actually, maybe you know this. There should be a Rust tool that forces you to write all those drop statements, but maybe that would like clutter your code base or something. So I don't know. I like drop. This is bad. Oh, right. This is cool. So there's other ways to drop things, and you can drop them with scope. So this is allowed. You have an internal scope. And then this is disallowed, or okay. Can't do this because B does not persist out of scope. And I don't really know like a more graceful way to get this to look, but I guess you could evenly indent them. Maybe that's like less cursed. This is more annoying.
More confusing.
Okay, well, I don't know. I think that's kind of cool.
I'm having trouble seeing the point of limiting your own scope within a function.
You don't have to manually use drop.
There's a couple specific. If you're using a mutex lock, you can use that for your critical section too. That's something I see a lot.
The real thing is you can.
And you can also assign variables to scopes. And because Rust is an expression-based language, right? That's why we don't need the return. We can just do something like that. Let's do that when you add a semicolon, because now it's an assignment. Yeah. And now, it's still not going to work, but
But it'd be cooler if it did, right? Wait, why is that not returning the box?
semicolon at the end makes a return unit.
Here?
Yeah.
Oh, I see. Yeah. There we go. So I mostly like scope for this. You can like build a variable in multiple lines, which is kind of cool. Have you used it practically for anything other than?
I use it like this, usually, like building a variable.
And you can put this in a match statement.
Yeah.
This can be a return statement.
It's pretty useful.
Yeah.
It's just nice. It's just a nice way, just another way you can have organized code a little bit nicer. So you don't have like these functions that are just meant for like creating this one variable because you don't want to do it like in like
Yes.
this one function. So you
Yeah.
still want to keep everything separate, you know.
Okay, this slide is the only time I'm going to say anything nice about C++. Is that true? Yeah, I think that's true. Resource acquisition is initialization. When you say box new, two things happen. You both get some memory back, and that memory has some values copied into it. This occurs, we'll say, atomically from the perspective of the language. Obviously, it's not well, okay, maybe not. It is not the case that it is atomic from the perspective of the hardware, but that is not relevant to us as programming language theorists. It could be relevant to us as security researchers. You're not allowed to persist a reference after deallocation. So let's take a look at this. And we pointed out that I have no idea how to use semicolons in Rust, so I figured this out when I was writing this code this weekend, and I labeled exactly where the semicolons are with statements because my eyes do not perceive semicolons. Okay, so let's take a look at this one. Okay. I guess this is basically the examples of the two things I just showed, but here we are. So we're going to box up Hello World. Hello World is going to run into a brick wall right here at the end of its scope. When it runs into the brick wall, it will transcend this mortal plane. But we still have its home address, right? So a few weeks later, I turn up at Hello World boxed house. Why did I box an array?
I don't ask those kinds of questions anymore.
Yeah, it's not worth it.
It made sense to me at the time, right? Like, okay.
I believe you.
So I make an array and I jam the array in a box. Not a vector, right? I didn't use a vector anywhere. Okay. No semicolon here, so this is the return value of this expression. So maybe return's the wrong word. This is the value of the expression. So the value of the expression becomes the value is aliased to x. So when I refer to x, it refers to the location y0, which refers to this y. So I'm dereferencing into hello. Okay, so I'm sure this code will work. Oh no! Oh no! Y doesn't persist. So what I have to do instead is like make a static or give it some different scope or location. So, okay. Rust attaches a lifetime to each reference. I'm going to make a claim that I believe is correct, but I had a hard time telling. I believe a lifetime is a set of scopes, and by default, it's just the current scope. And if it's static, it is the universal set of scopes. But you are able to interface with the type checker using lifetimes with aliases, and those aliases that will then capture some set of scopes. And the set of scopes they capture will be the set where objects of that lifetime are referenced. Lifetimes prevent use after free and go further to provide memory safety, and they do so by piggybacking on type safety. So this is pretty cool. To me, when I started using Rust, until I ran into lifetimes, which, to be clear, I don't like and try to avoid using, are nevertheless interesting because they've used the type system to solve memory safety problems, that's pretty cool. I think that's objectively cool. I suspect that if you were like really good at Rust, you would use lifetimes not that often, but when you would use them, they would save just enormous amounts of code, probably hundreds of lines. So anyways, that's cool. And so that's just at the tail end of this class, we showed the static lifetime, but you can look into lifetimes more. And I think I linked them here. You can look at this. Okay. We are now going to interface with dynamic memory allocation. There are pros and cons to dynamic memory allocation. It incurs overheads to performance. It incurs engineering overhead and design. Not in scope for this class. It is a catastrophe for real-time computing because it leads to wildly unpredictable response times. It is very, very hard to predict when you call malloc how long it will take for malloc to return. Usually you are entrusting an MMU to pass you back a value. Usually you do not have firm characterizations on the MMU. It is very unlikely you know how heavily memory is utilized at any given time. So at least when I was writing safety critical C code, we simply did not use dynamic memory ever. We did everything with statics. This led to a minor problem, which is that without dynamic memory, you're not Turing complete, which bothers some people. So it is true that without dynamic memory, we do not have computers by definition. But you can kind of do lots of things without being Turing complete, and I think people often brush aside how powerful a device can be without being Turing complete. So you don't really need to worry about that too much, other than now as an operating system, you are providing dynamic memory allocation as a service to your users. So you're simply required, or perhaps you are requiring yourself to be able to require this. So dynamic memory is required for variables that have a dynamic lifetime or a variable size. Now, I want to point out what I'm saying here, dynamic lifetime. This is a lifetime that is not known at compile time. If it is any set of scopes but can be known at compile time, then it is sufficient to give it a type-safe lifetime. So this has to be a lifetime that is somehow dependent on the control flow path or the numerical values that are being passed through the device. So its lifetime might change in response to I/O events. And it is also required for variable size devices, or variable size variables. This is true. I say variable size, but it means potentially infinite, because if there's some ceiling on the size of the memory object, then you can simply statically allocate it, though it might be very inefficient. I'm supposed to teach you about reference counting. I have seen reference counting in student code. I have never found a need to use it, but it appeared relatively elegant where I saw it. In Rust's ownership model, by default, something has precisely one owner. If you reference count it, it can have n owners for any n, and then is dropped when it reaches 0 owners. Things are already dropped when they reach 0 owners, so this is not too different. So this is just removing the upper bound on the number of owners. You can look into this if you would like. I've linked it here. Have fun. Vectors are also allocated. Here is an example of code that I actually wrote in real life. I don't know if this is good code. I would assume it's bad. But what we see here in this code is that I have a B-tree map. A B-tree map is probably in std. I'm sure it's in std. Or maybe it's in like collections or something.
Yeah, it's in collections.
And B-tree maps are cool because they are a map that preserves order. Which is, so it turned out I actually always wanted my maps to preserve order. And I'm pretty sure there is an ordered dictionary type in Python, but I'm like 100% sure at some point in like 3.10 or something, they just made dictionaries ordered and just like didn't tell anyone. And they told people that read the documentation, right? Like who does that, right? So I think big computer science is coming around on the idea that like if you put something in a dictionary in an order, it should stay in that order. And B-tree map provides that functionality. Nominally, B-tree maps would have worse worst case performance than hash maps, but I didn't feel anything. Okay. And at this point in time, we would be able to demonstrate something that our kernel cannot do, which is the vec macro. And in fact, vector new and vector from and all of these things. Vectors do not yet work in our kernel. And I think I can show that, but I would actually have to break my kernel, because unfortunately I just got vectors working while I was trying to eat my peanut butter sandwiches. So I didn't tell you this. So you know I'm like a peanut butter and jelly sandwich person, right?
Yeah.
I ran out of jelly, and so I'm on the peanut butter sandwich only train right now. That is mentally challenging. Like it was hard to get through the peanut butter and jelly sandwiches, and no jelly on there. It's like eating partially dried cement. But I did it for you, because I care about all of you and want you to succeed. Okay, so we can't do this. So we can just like remove our allocator. Okay. Let's go to lib. Oops. Yeah. Okay, perfect. So, there's like a bunch of stuff in here I don't think we care about yet. Okay, so here's my box. Wait, is it not working? Is there an error? No global memory allocator found, but one is required. Cargo toml? Ah! Is anyone else super annoyed by the presence of a cargo.lock and a cargo.toml?
What does cargo lock do again?
It makes sure all your dependencies have the same version for it. It's a quirk of the way package managers work. All package managers will have something like that.
Is it .cargo
cargo
config? Okay, I need to get rid of alloc. Okay. Okay. This will break. What? No, I gotta get rid of that. Source main. This is what happens if you break things badly enough. Okay. Okay. So I can't use boxes. Look at this line. How do I look at lines? There we go. Okay. This line is attempting to use a box. And I believe that's correct namespace for box. We can check. Undeclared type box, and then if I declare the type with alloc, it doesn't work. So I don't have the ability to use boxes yet. I don't have the ability to use vectors yet. So vec is not defined in scope. So working with your OS at this time, you're probably not able to use these wonderful memory management techniques. So vec is not in scope. Where does vec live? Vec lives in stud, but not in core. It's one of the things we lose when we switch to core. I would go so far as to argue it's why we switched from stud to core, because vec is going to require a lot of zhuzh to get itself working, and we haven't provided that zhuzh yet. And now, think very carefully about how you would spell zhuzh. Because
What's the spelling? I don't know what it is, but there is one.
there exists a spelling?
Mm-hmm.
Okay. Thank you. Okay. So, now what we're going to do is we are going to implement allocation gradually over time. And we are going to put back in all of the things that I just had to delete to get this example to work. So the first thing we're going to do is we are going to signal to the Rust compiler that we would like to resume usage of the alloc crate. The alloc crate is similar to core in that if we decompose stud into its components, alloc is one of them. But when we activate alloc, we become responsible for defining certain functionalities and features. And those functions, and basically that's the maintenance of the heap. So the functionalities and features are you must have a heap or something that can be used as a heap. So we are going to add a dependency to alloc, and we're going to do it first in our circlib. I did not know the convention of where to put this, so I selected putting it here. I don't know if this is reasonable, but we say extern create alloc. Is that correct? Yes. Okay. So this, in some way, signals to my crate that I want to be using things from alloc. Alloc contains boxed, which contains box. If I do this, we should update main so it doesn't contain any non-compliant code. There it is. Okay, can't find crate. So in order to completely and unambiguously communicate to Rust that we want to have the alloc crate here, we have to go back and undo the thing that I did previously, which is we have to edit our .cargo config.toml. And in the same place where we specified we need to compile from source components of the standard library, such as in this case we have compiler built-ins. You probably all remember when I told you not to use compiler built-ins and then you tried to do any memory operations at all. And you were like, to use for loops, I have to use this. And instead of building character and writing your code without for loops, you got me to start using compiler built-ins. So now my OS kernel is morally deficient. Okay, so in addition to core, we're going to add core, we have compiler built-ins, and we're also going to add alloc. Okay. And that's what it says. I'm just like roasting cargo for some reason. I don't know, I think it's reasonable that if I have to say extern create alloc in sorclib and also add alloc to a key value pair in my .cargo/config.toml, that seems like not the way to implement a package manager to me.
I feel like people who are using cargo are probably not the people writing operating systems, and it only seems to be pigeonholing people on writing operating systems.
If it's bad for writing an operating system, it's bad. This is why TypeScript is bad. What are all of these warnings? Are these new warnings? It just worked, right?
It's because it's running into errors before.
Yeah. Okay, so no global memory allocator found, but one is required. Link to stud or add octothorpe bracket global underscore allocator end bracket to static item that implements the global alloc trait. Credit where credit's due. That is a ludicrously good error message. That tells you exactly what you have to do. Like okay. So I guess that's a Rust C win because I'm not going to give credit to cargo here. Okay, so all we have to do now is figure out what the global alloc trait is. Okay, and then, so we gave some credit where it's due. Why do I have to implement this traits? Why can't I just write a function? Okay, so let's do that. Here's the change I made to my toml. Here's the error we get. And what are we going to do? We are going to create something that implements the global alloc trait. And some of these things might be linked. The global alloc trait isn't that bad. I'm actually not totally clear on how you infer from looking at this type of code which of these functions you have to implement and which ones you don't. I sort of had the intuitive sense that you're not going to have to write alloc0 and realloc yourself. That happens to be true, but I don't know how you determine that from documentation. So anyways, we're going to implement this, but we're only going to implement alloc and dealloc, and the other ones are going to be derived. Okay, alloc takes a layout. A layout is the shape of memory. So that is how big it is and what offset it can live at. It is going to return a raw pointer. And we, as the people implementing alloc, are responsible for ensuring that that raw pointer is to some memory that has been initialized and reserved. we as the OS are responsible for both the initialization and reservation. We're probably not initializing it by placing any value there. Probably what initialized and reserves means is we have to add it to the page table. So we're going to do that. Here is like maybe the craziest thing I've seen this term. Alloc doesn't return an option or result. It returns a pointer in all cases, and it just returns a null pointer if it doesn't work, which is exactly what the C programming language would do. And I made the case that the reason Rust is good at this is because it has option and result types. I don't know. Okay, that's my one comment. I said I only get one comment.
Why but you can answer a question though, surely. And I asked, why is it like that still if you have option return?
Oh, for portability and compatibility. So many systems expect alloc to work that way. And so there's sort of this like, I'll say it's implicit, but maybe it's POSIX compliant or something. I don't know. Do you know, Jimmy?
That wouldn't surprise me.
I was shocked.
I wouldn't be surprised if it was POSIX, but definitely compatibility. Yeah, so many
Yeah.
features expect things to work like that. It would be very difficult to not do that.
I do think the way I would have solved this problem is there's already these derived things. I'd have an internal Rust-only one that returns the option, and then I have a wrapper on it.
Yeah.
And I don't know why they didn't do
global
that.
alloc is supposed to, like, you're not ever supposed to actually explicitly use it, right?
Yes, but Rust is supposed to be written in Rust, right?
Yeah.
Like it is non-idiomatic to use a null pointer there. Okay, dalloc is free. I'm trying to be precise about my terminology here. This seems just wicked unsafe, right? Like I thought we were solving memory safety by switching to Rust, and I guess we kind of are because we're not exposing this to user level code. In order for dalloc to work, there's things that pass the type checker that it can't be called on. So any mute U8 that isn't the return value of alloc, you can't call dalloc on. And when you call dalloc on it, you must provide the equivalent, it doesn't have to be literally identical, the equivalent layout to which this was called on. So you as the programmer are responsible every time you call alloc, you have to save that layout somewhere so you can deallocate it later. And I guess I didn't actually check because you don't actually use these things directly, right? The way this works is the compiler deals with everything, and we never actually call alloc and dalloc, but that is sketchy. So that's my take. Yeah.
I think whether that it doesn't depend on the allocator you're writing to. Like I'm pretty sure on Linux it just uses malloc sometimes, which in that case the second layout's not going to matter because I'm pretty sure malloc.
It has to product to the same value.
Yeah. And usually that gets passed from the type system. So if your program is type safe, that's completely safe. If it's not and you're messing with that, you should hopefully know what you're doing anyways.
Yeah. No, like it's not surprising to me it doesn't cause problems.
Yeah.
But it is surprising to me how bad it is.
I get why it is the way it is.
Yeah, no, I don't have a
I don't have a better solution.
I definitely would do the wrapper thing on alloc. Alloc 0 is equivalent to calling alloc and then setting the allocated memory block to 0. Why? So, in the olden days, this was like an expensive memory operation, so this didn't happen. It is just strange to me that modern devices do not just zero initialize everything and don't ask you.
Go does.
Yeah, because Go's like not ancient.
Yeah.
So yes, so non-prehistoric languages do this, right? And I think like some really high-level stuff like, no, yeah, NumPy doesn't zero initialize, right? So I have seen bugs, yes, in AI 101 this term, I saw students who were confused because NumPy doesn't zero initialize its arrays. They just like made a NumPy array, didn't look at it, did some calculations, and they're like, wow, the output appears to be truly random every time. I was like, that is correct. And so like this is weird. So zero allocation is catching on. It's probably supported. What's this one do? Yeah. Calc. So Calvin allocating things sets them to 0. And I don't use calc out of spite because I think it makes writing C code too easy. But you're allowed to use it. I won't judge you. If you never use calc or realloc, I will mention that on your letter of recommendation, that you don't take shortcuts. Okay. So our job now is to create an allocator. We're going to create a really easy one. We're going to use this trick where we're not actually going to allocate anything, and we're just going to explode when anyone uses us, but we'll get to compile. So this is a really fun thing to do with your friends and family. So I'm going to go ahead and I'm going to make an allocator module, and I'm going to declare pub mod in my circlib. Nvim circlib. We got a bunch of pub mods, right? So go ahead and make a new one. Pub mod allocator. I was very tempted to name this something else, and the two competing things were alloc, which is a namespace collision, and alligator, which I don't know how to spell. Okay, so then once we declared that pub mod, we're going to go ahead and edit allocator.res. What are we going to do in here? Well, we're going to create a zero size struct, which you've probably seen these enough times now. You'll remember I implemented my version of println with a zero size struct. Maybe you all did as well. So zero size structs are a sort of good way to get things going. So we're just going to declare a pub struct. We're going to call it dummy. Pub struct dummy.
There, I can talk about it later, but there is a new allocator thing that's still unstable. It's not because there's a difference between allocators and the global allocator have two different uses, and the non-global allocator that you can implement for like arenas and whatever does use results and options and all these.
Well, yeah, because it's Rust internal, right?
Yeah.
Yeah, it's solving a different problem. Yeah, I'm still trying to come up with the assignment that teaches arenas, because I feel like that's a very Rust thing, and it's not a C thing. So I don't have like an assignment. Well, I've never used them.
Really?
Yeah.
I know the people that like really like C will tend to do those kinds of like memory reuse, arenas kind of stuff.
Yeah, maybe I wonder if I just don't think of it as an arena, because I do like recycle allocated memory all the time, and I guess that's arena by definition.
I would call that arena.
Yeah. Once you begin to perceive memory as just like some block somewhere, right? I don't know. Okay, so we got our dummy struct, and what are we going to do with our dummy struct? We are going to implement the mandatory traits. I love Rust. I don't know why I have to keep writing functions as traits. It doesn't make sense to me. I feel like everyone wrote a little bit too much Java, but here we are. So we are going to implement the global alloc traits for dummy. Do I want to type these? I'll type them so I can narrate them as I'm doing them. Okay, so these traits are unsafe for reasons that hopefully we have belabored enough at this point. It is common to do the sort of like use alloc, whatever. I don't like doing that because I am trying to keep track of the namespaces cognitively. So within the alloc trait, there is an alloc module, and within that module is global alloc. Global alloc we know about because we were instructed by an error message we are required to implement it. So we are going to implement global alloc for dummy. Oh, we're going to do capital D dummy. Why is it capital D? Because it's a class, and I understand this is not an object-oriented language. This thing is definitely a class, right? It has nothing in it, and we're writing traits for it. So this is a class. Sorry, Rust, you're object-oriented. I wanted you to be functional too. It's your fault you're not functional. I definitely could have made this work functionally. Okay, then we're going to have an unsafe function in here. It's going to be alloc. It's going to, okay, so does anyone want to argue that it's not object-oriented when I'm passing myself? Okay, all right, good, okay. Then we're going to pass a layout. We are not currently using the layout. Because we are a dummy allocator, we're going to do the same thing no matter how much memory people ask for, which is we're not going to do anything. But that layout is of type alloc crate, alloc module, layout. What is this going to return? It's going to return a mutable reference to a U8. We're returning a bunch of bytes. What is it going to return? We're going to return core pointer, null, null mute. What is that? That is a null pointer that is of the mutable pointer type. So that it is a mute U8 to match our type checker. We're matching our type checker. And this is provided for us within core. We already have core. Core is provided. So if I were writing C, this would say return 0. But we have to pass the type checker. So that's what we're doing. Then we have unsafe function Dalek. This is going to have the same type, I believe. Did I make that up? No, it's going to get the pointer back. So it's also going to get back a star mute U8 pointer. And we are going to ignore the pointer because we're not doing anything. It is not going to have any return type, which makes sense. We would not expect this to return. Now, if I were writing Rust-like code, which I'm not, right, because this is some interface to some non-Rust universe, I would expect this to return something, which is probably going to be a result. It should probably return an OK if the deallocation is successful. We're not doing that. We're ripping a panic. You can be more specific if you want. Okay. And then we're going to close this. Unexpected parameter name. Expected?
We did star mute U8 pointer, 7 pointer, star mute U8.
I did. That's not even. What did I open? Main. Okay. Oh, I wrote C.
Yeah, you wrote C.
That's so surprising I would write C at this point in time. Rust. Okay. All right, cool. No global memory allocator is found. Okay, so our code did not explode. These things, I don't think we care about this stuff that much because we're going to need a frame allocator and a mapper pretty soon anyways. We still don't have a static item that implements the global alloc trait. That was the thing we were working on, right? Because what we did is we wrote the allocator, but we didn't actually create an instance of it. So we're going to create a static. I think I'm going to call it a dummy. It's going to be of type dummy. And then I'm going to say that's a, is it lowercase? Yeah, lowercase. Cargo R. No! Help provide definition for the static. How do I initialize one? It's on the slides. Oh, I just say it's equal to dummy. Okay. I'm just going to copy this instead of trying to type it again. Okay, so what do? I create something called the allocator. I make it of type dummy, and I make it an instance of dummy. Kind of silly thing going on here because this is zero type struct. I don't have to initialize any of the fields within it because there's no fields within it. It is just sort of a collection of things I would call functions that look an awful lot like methods to me. And would you look at that? We have hello world back. So that is how you get the dummy allocator working. Let's see, function f11. So I at least got hello world after I updated .config. I add alloc and allocator both to source lib.rs. So alloc is the external crate, and allocator is my implementation of that crate. I defined a struct that contains some methods, specifically it contained alloc and dalloc, and then I declared a static of that struct. And from there, you can create a kernel heap, which will be the first component of your lab next time. Wait, are we out of time?
Maybe 3 minutes.
Yeah, I'm not going to start anything with 3 minutes left. So I actually have a note, you can't see it because I deleted it, that said I thought I was going to run out of time here. So I want credit for that, okay? Now, I deleted it because I thought I would get through it. I was like, maybe I'm going to get through it. But I didn't know how annoying I was going to be today. So credit to me. So the kernel heap is pretty cool. I got all this stuff working. I don't think it was too bad. Wait, is this clipping? Which one clipped? That one. Okay. I use options instead of results. Okay. Yeah, I think this looks fine for you. Once you finish the lab on Wednesday, which some of you have probably like de facto done already, then you will have vectors back. I basically wanted you to have vectors before giving you the final assignment, which I think I'm going to ask you to implement Snake. And those of you that want a more systems-oriented assignment, I'll probably just tell you to implement all 3 of the allocator types yourself and give you credit for that. So that's the plan for the rest of the term. I don't know what lecture is going to look like next Monday because I think I'm just going to introduce the final. And I don't know how long that's going to take because I haven't done the final yet myself. But I assigned a very similar final once, and I think it was fun. So that's the plan for this term. Thank you, and have a nice day. Oh, don't be, wait, no question. Is it for class?
Do you expect the work on the final to be done entirely during the final block, like the 2 to 5 p.m. on whatever day? Or
Oh, no, you can do it whenever you want. Yeah, it's I can turn a final project that is due at that time.
Okay.
Yeah. Thank you. Okay. Ask me any questions if you have them.
I won't be here Wednesday.